Okay, now we are recording. I won't say everything again, but just to say that we are here today for the defense of Matheus, who is a master's student at PESC. For the defense committee, we have Professor Towsley at UMass and researcher in Portugal from LNCC here in Brazil. And I was saying that it's a pleasure to have the two of them participate in this committee. And I'd like to thank both of them for taking the time to be here with us today to evaluate this work and give their contributions. So the way it works is Matheus has between 35 and 40 minutes to do his presentation. After that, the committee will make questions to Matheus. And after that, if somebody in the audience wants to make any questions, they are welcome to do so. And then after that, the committee has a closed deliberation, and the result is announced in this room. And everybody that is participating has to keep their cameras and microphones off, please. Include us in the committee so that we can hear and see Matheus better. So I think that's it. Franklin, do you want to say anything else?
No, Daniel, thank you very much. I don't have to add anything to what you said.
Okay, and I think we're all set. Without further ado, Matheus, it's all yours.
Okay. Well, shouldn't we say that we agree for this dissertation to be?
Yeah, we that's a good point, but we have some written statement now that I think is sufficient.
Okay.
In Igor's defense, we did that, right? You're right, but here I think we have some written agreement that we all agree. Okay, so I think it's okay.
Okay. So can you all see my screen?
Yes, but it's not in full screen mode.
Sure. So let's start. Good morning, everyone. Thank you all for your presence and time. Thank you, Don and Renato, for accepting the invitation to be part of my examination board. My dissertation is entitled Characterizing the Inherent Relationship between Unitary Quantum Walks and Non-Homogeneous Random Walks on Finite Graphs, which was a research enterprise jointly advised by Franklin Marquezino and Daniel Ratton. Quantum computing is on the verge of a breakthrough, promising a revolution in science and technology. Differently than classical computers, quantum computers do not rely on transistors to abstract logic. They harness the quantum properties of nature to perform computations. The peculiarities of quantum phenomena allow quantum computers to solve problems that are really hard to be solved in classical computers. As a great example, we have the most famous quantum algorithm, Shor's algorithm for factorizing integer numbers in polynomial time. This powerful algorithm characterizes perfectly the dichotomy between quantum and classical computing, as it is capable of breaking the cryptographic systems in which digital communications were built upon. Among the challenges for the future of quantum computing, the design of quantum algorithms is critical. In this context, quantum walks are one of the few tools for the development of quantum algorithms. Quantum walks can be seen as a quantum diffusion process on the edges of a graph. Among their applications, quantum walks drive efficient solutions for problems like searching for marked vertices on the graph and to simulate physical systems that are described by sparse Hamiltonians. For me, the most amazing thing about quantum walks is that they form a universal set for quantum computing. This means that any quantum algorithm can actually be implemented through quantum walks. To be precise, quantum walks were developed to be, or designed to be, quantum analogs of classical random walks. Classical random walks are stochastic processes defined on the vertices of the graph. They are a fundamental building block for a myriad of algorithms in classical computing, which exploit the simplicity of the description of Markov chains. A great example that depicts how ubiquitous random walks are in classical computing is the web surfer model. This algorithm is used by Google search engine to recommend web pages for billions of users every day. The web surfer model is nothing more than the simulation of a random walk on the web page graph. Much of the literature on random walks goes towards time homogeneous random walks. Time homogeneity allows analytical tractability for random walks. Among the famous known results, we have the conditions for the convergency probability of random walks. To give you some visual intuition on why homogeneous quantum walks and random walks are different, I prepared this brief animation depicting the evolution of a quantum walk and a random walk on a cycle. Here, in the top figure, we see a Hadamard walk on a 100 vertex cycle, and on the bottom figure, we see a uniform random walk on the same cycle. In spite of the fact that the evolution in time of both processes is symmetric, we see that the behavior of the spread is completely different. And this motivates the question that encapsulates all of our research efforts in this work. Are time-dependent quantum and random walks statistically equivalent? As an example, can we construct for the quantum walk on the top figure a random walk with the exact same vertex probability distribution? And also, can we construct from the random walk depicted in the bottom figure a statistically equivalent quantum walk on the same graph in terms of the vertex distribution? Our contributions address this question, providing a positive answer. Our first contribution is a procedure that constructs a statistically equivalent random walk for any discrete time point quantum walk. This result is also valid for the case of multiple quantum walkers that interact with each other in the same graph. Our second contribution stems directly from the first. It's a novel procedure to simulate quantum walks, denoted quantum walk trajectories. Our last contribution is a procedure that goes in the opposite direction of the first. It enables the construction of a statistically equivalent discrete time coin quantum walk for any given random walk. Let's then address the mathematical background we need to talk about those contributions. The graphs we're interested in here are directed symmetrical graphs in such a way that if the edge UV exists on the graph, the edge VU will also exist on the graph. We can define a non-homogeneous random walk as a process on a directed graph that diffuses a probability distribution over the vertices of the graph through its edges with time-varying transition probabilities, for which holds the Markovian assumption. In a formal way, if we use pi of t to denote that probability vector such that the vth coordinate of pi of t is a probability of finding the walker at vertex v for a given instant t, we can construct a stochastic matrix by defining the transition probabilities to leave from a vertex u and arrive at vertex v at instant t, which are denoting p sub vu of t, such that we can compute the probability of a vertex v at instant t plus 1 by summing the probabilities of being on a vertex u at instant t times the transition probability to hop between these vertices. From the probabilistic formalism, if we sum up the probabilities, the transition probabilities to leave from a vertex, we need to have 1, and we can condensate this stochastic description in the matrix equation that appears in equation 3. Simulating random walks is pretty straightforward. We can simulate a random walk by drawing a vertex from the initial vertex distribution, and then at each time step, we draw a neighbor of the current vertex with a probability given by the transition probability to hop between these vertices. As an example here, we have in this simulation that the first vertex drawn was vertex 5. On time step 1, we draw neighbors vertex 6, which is a neighbor from vertex 5. In time instant 2, we draw vertex 7, which is a neighbor of vertex 6. And all of these neighbors were drawn with half probability. And when we consider the whole behavior of the simulation, what we see is a path of the graph, which we call sample path. Now, random walks can be defined as an evolution process of a complex vector in the Hilbert space H sub W, which is actually a subspace of the tensor product space between two other Hilbert spaces, H sub V, which codifies the vertices of the graph, and H sub C, which codifies the degrees of freedom in which the quantum walker can move on. Clearly, these subspaces are defined by the graph structure. We can represent this quantum walker using the canonical vectors of Hilb sub W. Each edge of our graph will be represented by one of these canonical vectors, in such a way that if we take the set of all edges, what we have is a basis for H sub W. The Walker system state will be defined by a unitary vector, cat psi of t, which can be described generically by a superposition of all the edges of the graph, each modulated by a complex number, which we call the wave function. The quantum walker evolves by the application of a unitary operator SW, which is actually the product of two operators, the coin operator W and the shift operator S. And they will define completely the dynamics of the system. We can think that a coin operator acts by mixing the wave function amplitude between or among outward edges through complex multipliers. We can define the global coin operator by defining for each vertex its specific coin operator, which we're denoting here by W sub V. And then we combine this specific coin operators for the vertices using the tensor product operation. To give you some visual intuition on how the coin works, let's consider that our initial state is a localized state on an edge. We are here considering a 5x5 grid graph. So our initial state is, let's consider that the center vertex is the vertex V, and we are putting all of the wave function incident to the edge VC, which is here denoted by this red edge. Once we apply the coin operator, what we will have will be a superposition of all the outward edges that comes from V, each modulated by its particular specific complex multiplier. In turn, the shift operator acts by moving the complex amplitudes between outward edges. It actually creates the flow of the wave function. Mathematically, we can define a shift operator by mapping a state UC into a state VC prime, such that U and C are neighbors in the graph, and C and C prime are codifying the degrees of freedom of U and V respectively. We can define this assignment behavior in a generic way by considering two auxiliary functions. The function eta that gives an ordering for the outward neighbors of a vertex, and the function sigma that actually defines which outward edge will be mapped to which outward edge. To give some visual intuition again on how the shift operator works, let's consider once more the 5x5 grid where the center vertex is denoted by vertex V. In this figure here, the color of the edge is codifying the edge direction, such that the red edge is pointing upwards, the blue edge is pointing leftwards, the green, and so on and so forth. So we can define a shift operator that maps the upward edge of V to the upward edge of the upward neighbor of V, the leftward edge of V to the leftward edge of the leftward neighbor of V, so on and so forth, codifying the moving shift operator. Or we could also map an edge VU to the edge UV, creating the flip-flop operator that appears here in figure C. These two operators will be mentioned further ahead in the presentation. Finally, to embed probability in quantum walks, we need to consider measurements. Measurements are non-unitary projective operators that collapses the wave function and breaks superposition. By breaking superposition, we kill or we annihilate the quantum interference that actually defines quantum walks. To measure the system, we need to define a basis. And since we are interested in measuring the Walker position, the basis that we use to measure the system is the canonical basis of cube sub h sub w. When we say that we measured a position VC, the edge VC at instant t, we mean that after measurement, the state of the system is VC. And if we measure the system again and again, what we will have is VC over and over again. From measurements, we can define two probability distributions. The state probability distribution rho that assigns the probability to measure a state VC at an instant t with the squared absolute value of the wave function incident in that state for that particular time. And we can define the vertex probability distribution upsilon that assigns the probability of measuring a vertex V at instant t by the sum of the probabilities of measuring all outward edges of V in that particular time instant t. To actually understand which events are captured by rho and upsilon, we need to consider the collapse of the wave function. Rho of VCT is a probability of measuring the state VC in a Walker state that evolved unitarily until t. This means that you are not allowed to perform any measurement on the system between times in instance 0 and t if you want to have rho of VCT as described before. If we, in the same fashion, rho VCT plus 1 relates to an event of measuring the state VC in a Walker system that evolved unitarily until t plus 1. If you want to observe the system at instance t and t plus 1, what we actually need to do is to prepare two independent systems in the same initial superposition of the edges, evolve the first system until time t, the second system until time t plus 1 independently, and then measure both systems. And if we want to consider the case of multiple Walkers, the postulates of quantum mechanics say that we need to enlarge our state space representation by tensor product operations. Let's assume that we have k quantum Walkers. The space in which they will live is q sub h sub w to the k, which is the tensor product of q sub w with itself k times. We'll then note bold u and bold c to be k tuples of vertices and degrees of freedom. If we consider a canonical vector of cube sub w to the k, what we have, in fact, is a vector that codifies k edges of the graph simultaneously. Again, if you take all the possible simultaneous configurations of edges for the graph, we will have a basis for this enlarged Hilbert space. Once more, our Walker system is represented by a unitary vector in this Hilbert space, which can be generically described as a superposition of the edges of the graph. each one, where each edge is actually weighted by its wave function. In this scenario, rho of bold C, bold V, and T is the joint probability for all the k-walkers, for measuring all of the k-walkers in a particular combination of edges. And then upsilon of bold U and T is the joint probability of measuring all the k-walkers in a specific combination of k vertices of the graph. To address quantum simulation, let's consider what are the implications for measurements for the functions upsilon and rho. If you want to measure a given quantum Walker system k times, what we need to do is actually prepare k identical systems and then evolve each of these systems up until a particular time instant and measure all of the systems. We can depict this behavior in a figure like this, where the y-axis gives the vertex outcome for a given time instant, and the x-axis represents the time instant in question. Here in this figure, each colored circle is representing an independent measurement or sample of a quantum Walker system. Since all of these dots or circles are independent, there is no guarantee that adjacent circles in time will be neighbors of each other in the graph. This simulation stems from a cyclic graph in such a way that if the y-axis distance between two adjacent dots in time is bigger than 1, they are not neighbors. As an example, the orange dot here and the green dot here are representing vertices that are not neighbors of each other. And that came out as a result of measurements in time instance 1 and 2. So if we're considering discrete time quantum walks and non-homogeneous random walks, we can ask the first fundamental question addressed by this work. Can a random walk match the evolution of a vertex probability of a quantum walk? And the intuition behind why we can answer this question positively is that random walks are a diffusion of probabilities on the graph vertices, while quantum walks are a diffusion of wave functions on the graph vertices. Since wave functions map naturally to probabilities, what we have to see is whether or not the probability distribution upsilon can actually be described as a local evolution of probability from a given random walk. Let's consider the conditions for this equivalence in a formal way. We will consider that the probability vector for the random walk is such that its vth coordinate in a given time instant is the probability of measuring the vertex v in a quantum Walker system for that particular time instant. Then we need to show that it exists a transition probability matrix P of t that makes upsilon v of t plus 1 be given by a combination of upsilon u of t, where u are inward neighbors of v, and where each probability is multiplied by the transition probability to move from u and arrive at v for that particular time instant. It then follows our first theorem. I'm not gonna enunciate it completely, but to condensate, we state that the action of a unitary operator SW that codifies a quantum walk is equivalent to a Markovian matrix PT constructed in this way. We'll address the probability to move from vertex U and arrive at vertex V at a particular time instant t by the ratio between the probability of measuring the quantum Walker state Vc at instant t plus 1 by the probability of measuring the vertex U in the quantum Walker system at a particular time instant t. Whenever this vertex probability is bigger than 0, and there is, in fact, an edge between u and v in the graph. When this edge exists, but the probability of matching the vertex is 0, we're simply gonna define the transition probability to be 1 over the degrees of u. If none of these conditions are valid, we'll just put the transition probability to be 0. If we do so, we show that, in fact, this random walk is recovering upsilon in its probability vector for all time instants. The question that comes after this theorem is whether or not we can extend this result to the case of multiple interacting walkers. If we're considering walkers that do not interact with each other, the answer is trivial. We can extend this result because in this scenario, the walkers are all independent of each other, and we could construct for each walker the respective random walk specified by theorem 1, and then compute the joint probability by multiplying the probabilities of the walkers. To account for interaction, we need to change the description of the time evolution of the quantum walker by introducing a new operator that will do the interaction between the walkers, which we'll denote by u. So u is a unitary operator that is capable of letting the k walkers interact with each other. The only type of interaction that u does not allow is to move the walkers, because we want to restrict this behavior to the shift operator. In this enlarged scenario, the coin and the shift operator are simply obtained by taking the tensor product of the coins and shifts for each of the walkers. And the intuition behind why the result is valid in this case comes from a trick. We'll construct a larger graph which the vertices of this graph will actually represent the simultaneous positions of the k walkers together. The vertex set for this new graph is simply v to the k. Each vertex of this graph will be denoted as a bold v, which is a k tuple of vertices of G, and this means that, well, for this tuple, the jth coordinate is the position of the jth walker. Each edge of this enlarged graph will correspond to a joint movement of the walkers, and the degree of the vertex tuple, in this case, since we're defining the edge to be representing the joint movement, the degree of the tuple will be the product of the degree of the vertices forming that tuple. The not so good news is that this graph grows exponentially as we increase the number of walkers we're considering. To illustrate this graph, let's consider a case of two interacting walkers in a 10-vertex cycle. Here, in the left, we are depicting the cycle, and on the right, we are depicting the neighborhood for one of the tuple vertices of G prime. We can see that each of these vertices are actually representing the positions for the first and the second walker, and that an edge between two vertices gives a combined movement for the walkers. Such like, as an example, if we take this edge here, this edge represents that when we hop from this vertex to this vertex, the first walker moved from position 0 to vertex 1, and the second walker moved from vertex 0 to vertex 0 itself, so it remains still. Then we can enunciate the theorem that goes almost exactly the same as the previous one, where the only difference is now that we're considering the interaction operator U, and V and U here are actually representing vertices of this enlarged graph, and C is representing a tuple of degrees of freedom. So to actually show these theorems, we had to stipulate time-dependent probabilities. It's from this time dependence that we are able to recover the quantum behavior. We cannot do this by taking homogeneous random walks. The good news is that we enunciated these theorems without taking any assumption on the time independence of the quantum walker. This means that these theorems are valid for quantum walkers that have the unitary operators S, W, and U changing with time. Okay, but we saw that the way that we simulate quantum and random walks is fundamentally different. So what are the implications for quantum walk simulation when we consider the theorems we just shown? The answer is straightforward. Now we can actually simulate the quantum walk by simulating its statistically equivalent random walk. To illustrate this, let's consider a Hadamard walk on a cycle of 20 vertices with moving shift operator for the first 10 time steps of the process, with initial condition given by an equally weighted superposition of the outward edges of vertex 10, where the only difference between them in the superposition is a complex phase. If we sample this system using the usual procedure for quantum walks, we'll have the figure we saw before, okay? Where the samples are independent of each other. Now, if we use its equivalent random walk, what we will see is a very nice figure. It's a figure that depicts trajectories of the graph, where each of the samples that we draw from the quantum walk are actually paths in the graph. So each colored line here is representing one trajectory, a path in the graph. And it's clear that since it's a cycle, every adjacent vertex drawn in time, in adjacent time instance, will be adjacent in the graph. We define this method as the quantum walk trajectories method, which sample paths of G that recover the quantum behavior with convergency ensured by the law of large numbers for the vertex distribution. And this is true for every time instant. To depict this convergency behavior in a numerical way, we can compute the total variation distance between the empirical vertex distribution in an ensemble of trajectories and the vertex probability distribution upsilon of the quantum walk. In this figure, we see the total variation distance displayed on the y-axis, and the x-axis gives us the time of the process. We see that as we increase the ensemble size, the total variation distance value decreases. In fact, for each one of these lines, we have this fluctuation on the value of total variation distance because the variance of the upsilon distribution is not the same throughout the evolution of the quantum walk. But is it efficient to actually compute the quantum walk vertex distribution with the quantum walk trajectories method? Sadly, the answer is no. And it is so because to construct the random walk matrix for a time instant t, we need to have the value of the wave function for the next time instant. And if we have the value of the wave function for the next time instant, we already know what the probabilities are. To illustrate this, the complexity of constructing the matrix matrix when we have the wave function is the number, the time complexity is the number of the vertices in the graph squared. When we do not have the wave function, then computing the wave function becomes the bottleneck of the problem. And the complexity is then t times the number of edges of the graph squared. Nonetheless, if we consider specific coins, shifts, and graphs, the problem is easier. We've shown that we can compute these transition probability matrices for a Grover walk on a d-dimensional torus in time complexity t times the number of vertices in the torus times the dimension of the torus squared. More generally, we also show that if we consider quantum walks with time-independent unitary operators, we can use the spectral decomposition that uses a simulation procedure of time complexity t with time complexity t times the maximum degree of the graph times the number of edges. Our last fundamental question then is, can a quantum walk match the evolution of vertex probability of a random walk, of the vertex probability of the random walk? And if, as a matter of fact, this question has a trivial solution if we allow the quantum walk to be measured at all time instants. The annihilation of the wave function and the loss of quantum interference collapses the quantum walk to a random walk. As an example, it is well known that the Hadamard walk on the cycle will collapse the uniform random walk on the cycle if we measure the Hadamard walk at all time instants. So we evolve the system one step and measure, evolve the result of measurement one step and measure, so on and so forth. Nonetheless, we're really interested in defining a unitary process, in finding operators S and W such that the evolution of the quantum walk matches the evolution of the random walk. And the postulates of quantum mechanics will lead the way to find a proper solution. The first thing is that we need to represent random walks in the Hilbert space of quantum walks. We need to find a unitary representation such that the probability of measuring vertex V at instant t, of measuring the quantum walker at a vertex V at instant t, will be exactly the random walk probability of measuring that vertex V for that particular time instant t. The good news is that what we want is a map between the probability simplex to the complex hypersphere, which there are infinite valid maps that accomplish what we want. The map we choose is the following. We'll define the wave function of a state Vc at a particular time instant t as a generic complex amplitude times the transition probability to move from an inward neighbor of V at instant time t plus 1, its value, the square root of this value, times the square root of the probability of finding one of the inward neighbors of V, vertex U, at time instant t minus 1. If we do this, we can simply check that upsilon V of t will be exactly pi V of t. So the vertex probability of the quantum walk will be exactly the vertex probability of the random walk. And we can put this in the vectorial representation by simply addressing to each canonical vector the respective wave function defined before. Our shift operator will be an operator that can be defined for every graph. We'll take the auxiliary function eta to be the ordering that such that the cth neighbor of V, it's actually the neighbor of V with the cth smallest labor. We'll construct the function sigma in such a way that we map the edge UV to the edge VU. And we call this operator S sub RW. This operator is nothing more than a version of the shift operator, of the flip-flop operator that I showed you in the background section. Finally, the coin operator will be constructed with a trick from linear algebra. We know that any basis exchange of the system can be made unitary. So for each vertex V, we will construct a coin operator for that vertex W sub V of T that maps the vertex that represents the inward probabilities to V at instant T that came from the inward neighbors of V at instant T plus 1 to the vector that represents the outward probabilities of V, the probabilities of leaving V at instant T. And then we construct the global coin operator by taking the tensor product of all of the vertex coin operators. Then we have our last theorem that defines this random walk. It states that for any stochastic matrix P of T, we can construct the shift operator S R of W and the coin operator from basis exchanges that will map precisely the evolution of the random walk to the evolution of the quantum walk, such that upsilon of U of T is exactly pi sub U of T for all U and T. To conclude, we established a formal procedure capable of constructing random walks that capture quantum behavior. This establishment allows us to define the quantum walk trajectories method, a novel quantum walk simulation that captures quantum behavior while respects vertex locality. In addition, we also established a formal procedure capable of constructing quantum walks that captures random walk behavior. And as final comments, we did so without harming any of the postulates of quantum mechanics. And we can think that what we've shown abstractly is that quantum and random walks are two faces of the same coin. There are two different mathematical descriptions capable of describing the same probability diffusion on finite graphs. Thank you.